this lesson, I invite you to dive in and explore the denizens of the deep with me. Those amazing reptiles that swam in the Earth's oceans while dinosaurs were running around on land. They were the Mesozoic marine monsters. As background, I'd like to consider the organisms that live in ocean ecosystems today. Animals like sharks and other fish, squid and jellyfish, shelled marine invertebrates like clams, underwater creepy crawlies like lobsters, shrimp, and sea stars. Guess what? All those organisms evolved in the ocean, and they've never left their watery worlds. For that reason, they are well adapted to their ocean-going lifestyles. Collectively, these creatures have survived 5 major mass extinctions over the course of geological time. They are survivors. There are notable differences between these marine animals and other kinds of sea-going vertebrates, like dolphins, whales, penguins, walruses, and sea turtles. This group of animals descended from those that first evolved in marine environments, but then innovated a new lifestyle on land. We call the big group of terrestrial vertebrates tetrapods, a name that basically translates to 4-legged land walkers. Amphibians are included in this group, as are reptiles, mammals, dinosaurs, and birds. Some tetrapods went even further with this innovation of land living and developed a suite of features that allowed them to break away from their tie to water. These tetrapods are called amniota. Unlike amphibians, which must lay their eggs in water, the amniotes are the animals that lay hard-shelled eggs or give live birth on land. You can think of either as a self-contained marine world that keeps embryos happy and healthy, but away from water. From this group of fully terrestrial animals, some lineages went back to the sea, evolving unique new specializations for life in marine systems. Why did this happen? Like most questions in evolution, the why is difficult to answer. Perhaps it was driven by resource availability or exploiting a new environmental niche. Like most changes in evolution, these were probably triggered by an accidental error in the genome, also known as a mutation, resulting in a new feature that can be tried out in different environments. Though we don't know exactly why organisms return to the sea, it's clearly a well-worn evolutionary pattern, since it has been repeated over many instances of convergent evolution. Let's take the example of 2 marine animals, a shark and a dolphin. At first glance, you might notice immediately their similarities. Both have torpedo-shaped bodies, dorsal fins on their backs, tail fins, and fins instead of arms. They're also even a similar color with counter shading, lighter on the bottom and darker on the top. And of course, they both swim. All of these parallels might prompt you to think that these 2 animals are really closely related. But except for the basic shapes of their external body traits, they're different in almost every other way. Consider how each animal breathes. Sharks breathe by swimming, mouths partially open, to move water across gills. Those gills have lots of tiny capillaries that allow them to extract oxygen from the water and exchange that oxygen with carbon dioxide coming back from the body's circulatory system. Dolphins, on the other hand, have to swim up to the surface and take in a deep breath of air. Their flow of oxygen takes place from the surface air and heads into the lungs, where gas exchange happens via alveoli, just like it does in humans. Then they must hold their breath when they dive back underwater, just like us. There are many more differences that are hidden just below the surfaces of their bodies as well. The bodies of sharks are made of cartilage, while dolphins have skeletons made of bone. The front fins of the 2 animals are also totally different. In sharks, the front fin is made of thin cartilaginous rays, like the fins of most fishes, while in dolphins, the front fin is a modified hand, made up of the same bones that are in our hands, just changed a bit by evolution, so there are more phalanges than we have in our fingers. Sharks don't have hair, but did you know that baby dolphins do? And finally, take a look at their tails. Did you notice that they're oriented differently? Dolphins have horizontal tails, while sharks have vertically oriented tails. All these differences add up to highlight the pattern of convergent evolution we can observe in these 2 swimmers. and in many other amniote groups over the history of life on Earth. For those amniote lineages that return to sea, the environment helps push the evolution of form toward the same basic good tricks that are well suited to water. One of the best examples of this is found in the fossil record of whales. You may not have ever thought about where whales come from, but their fossil record preserves an awesome story of gradual transitions from fully terrestrial wolf-like creatures with 4 legs and sharp carnivorous teeth to animals with shorter forelimbs, paddle-like hands, and a longer, more muscular tail. The pelvis gets smaller and separates from the backbone, allowing whales to use their whole vertebral column for swimming. Why? Because marine mammals like dolphins and whales evolved from land mammals that don't have backbones that bend from side to side when they walk. Instead, they have backbones just like those of modern running mammals, which undulate in a wave up and down rather than the wiggly side-to-side motion of fishes. With that under our belt, let's get up close and personal with some of the first groups of organisms that capitalized on this return to the sea strategy way back in the Mesozoic. These animals are pioneers. They were among the first amniotes to exploit aqueous ecosystems after a long evolutionary history on land. There are 2 things to remember about this period of time. First, the end of the Permian period and the beginning of the Mesozoic era was marked by a huge mass extinction event. The Permian-Triassic extinction wiped out an estimated 95% of all life on Earth, and it wasn't concentrated only on land. It had serious implications for marine life, too. From microscopic single-celled organisms to a whole array of marine invertebrates to a diversity of sharks and fishes, the marine world was decimated, just like the terrestrial world was. For any organism lucky enough to pass through that massive extinction filter, the other side was a world denuded of diversity, full of open niches where evolution could do its work. These ecosystems were ripe for the picking, ready to be exploited by terrestrial vertebrates exploring brand new land and ocean environments. And spoiler alert, everything about these ocean systems bears some cool similarities to the unexploited region of the air that we'll head to in the next lesson, as we lean into a discussion of pterosaurs, the flying reptiles that ruled Mesozoic skies. The second thing to remember is what the globe looked like. When we view this paleogeographic reconstruction of the planet at the beginning of the Mesozoic, one of the things you see is a world with great expanses of land and a lot of water. There were no polar ice caps during the Mesozoic era. When water isn't locked up in ice during warmer periods of Earth history, the outcome is more oceans. Just look at these vast amounts of marine ecosystems. The Panthalassa Ocean, the Tethys Sea. These ocean environments persist throughout the whole Mesozoic. They sometimes even included giant continental seaways, like the Western Interior Sea, that divided the North American continent in the Cretaceous period into eastern and western halves. The most straightforward way to tackle the diverse array of Mesozoic marine monsters is to start with their evolutionary tree. Here we can see the lineage of the now familiar amniotes, those fully terrestrial egg-laying and live birth animals. You can follow the branches to our own lineage, the synapsids, and to the group that we typically think of as reptiles, more technically called the diapsids. This group gets split into 2 big tribes, the lepidosaurs, including living lizards and snakes and all their close relatives, along with a lot of extinct animals, and the archosaurs, the group that includes crocodiles, pterosaurs, dinosaurs, and birds. Contrary to what our pop cultural world will have you believe, the swimming reptiles aren't dinosaurs. In fact, they aren't even archosaurs. In an evolutionary sense, we find them way over here, nested within the lepidosaurs, but clumped together with lizards and snakes. Though they lived alongside dinosaurs, the marine reptiles were not dinosaurs at all. The beginning of the Triassic witnessed what we can call an adaptive radiation, or a period of intense evolutionary innovation, when the survivors of the Permo-Triassic extinction event diversified in a very short period of time. Well, at least a geologically short period of time. It was in these early days that the very first land-based Triassic reptiles began to colonize the seas. The earliest seaward forays resulted in a bunch of cool-looking, weird early experiments with marine life. Animals like Tanystropheus, from the Greek words for long and hinged to describe its neck, showed up with its needle-like fish-eating teeth. Or consider Placodonts, Greek for tablet teeth. These marine reptiles traded out their sharp reptilian dentition for a mouthful of crushing plates, perfect for crunching up mollusks. The very first marine reptiles still had fingers and toes, though they may have had webbing between them and likely still spent time on shore. A key adaptation among these earlier experimenters with sea life was the innovation of retaining and hatching eggs within the body of the mother until the babies were able to swim and feed for themselves. This innovation allowed some marine reptiles to loosen their ties to the land even more fully. They no longer had to pull themselves up and out of the water to lay eggs, but could stay out, retaining their eggs internally, and eventually give live birth to well-developed young. This key amniote adaptation allowed marine reptiles to diversify even more. And by the Middle Triassic, we can already see the three major groups that would rule the oceans until the Cretaceous extinction 66 million years ago. They are the plesiosaurs, the mosasaurs, and the ichthyosaurs. One of the more interesting things about the marine reptiles is that they were actually discovered before the first dinosaurs were. Back in the early 1800s, people were just beginning to understand the importance of fossils. Instead of being thought of as decorations for the interior of the earth placed there by God, they were beginning to see them as the remains of animals that lived in ancient worlds. There was a huge amateur and scientific interest in the new field of undergroundology, with people all over the English countryside searching for these hallmarks of ancient life. On the British coast, a sequence of marine shale was the collecting ground for a young girl, Mary Anning. Mary had an aptitude for collecting the coiled ammonite shells then known as Amon's horns, and the internal hard parts of straight-shelled squid-like creatures called belemnites, known as devil's fingers. She sold these fossils as curios to help support her family. Around 1810, when Mary was just 12 years old, she and her brother spotted the strange, smiling mouth of the first ever found marine reptile poking out of the Jurassic-aged marine shales near her home in Lyme Regis. They dug into the hill, exposing a 5-meter-long skeleton that was eventually named Ichthyosaurus, from the Greek for fish lizard. In 1823, Mary did it again with another marine reptile find when she discovered a complete specimen of Plesiosaurus, meaning near to lizard. Remember, the first dinosaurs weren't consolidated into a group by Sir Richard Owen until years later, in 1841. Marine reptiles are often found in beautiful condition, preserved in 3D with all their bones still intact and articulated perfectly, each bone connected to its correct corresponding element. Since they lived and died in marine ecosystems, their dead bodies would often drift down to the seafloor, where, in certain conditions, they'd be spared from harmful processes like scavenging, bacterial decay, weathering, or disarticulation that plague carcasses on the land. Sometimes, if they were covered over by sediment quickly enough, bacteria wouldn't even have time to degrade all their soft parts. We found some really amazing fossils from these oxygen-poor ocean floor environments. The plesiosaurs are the Loch Ness Monster-style marine reptiles. They all have 4 fins built by elongating the phalanges, those little tiny bones that make up each joint of the finger. We call this hyperphalange, which just means crazy amount of finger bones. Plesiosaurs take this basic body plan and evolve into 2 main groups. The elasmosaurs are known for their very long necks and small skulls. Some of them may have had up to 70 vertebrae in their necks. The pliosaurs, on the other hand, are known for having shorter necks and humongous skulls. This type of variation points to some niche partitioning in this group of marine reptiles. Some plesiosaurs, like living whales, got huge and may have been up to 45 feet long. That's the great thing about living in the water. The constraints that limit body size on land are effectively gone. given the buoyancy of water. Plesiosaurs also have little conical teeth, perfect for stabbing fish, and were fearsome predators in Jurassic and Cretaceous oceans. We used to believe that plesiosaurs may have had to flop themselves out onto land to lay their eggs, but a few years ago, a new discovery shook up that old idea. The discovery of a well-preserved plesiosaur skeleton that included the remains of a plesiosaur fetus, probably in the process of live birth, when mom and baby died and sank to the seafloor. Our next group of marine reptiles are the mosasaurs. These beasts were prowling around in ocean ecosystems when the very last dinosaurs were ruling the late Cretaceous world on land. At first glance, it might be a little tough to tell a mosasaur from a short-necked plesiosaur if one was swimming past you at top speed. But strip away all the external features and get down to the bony skeleton, and there are some clear differences. Mosasaurs are very closely related to modern-day lizards like Gila monsters or monitor lizards. Mosasaur limbs have transitioned into webbed hands and feet rather than true paddles like we observed in the plesiosaurs. They still have real separation between their fingers and toes, and the tails of mosasaurs were broad and flattened from top to bottom, giving them a great propulsive tool in their underwater world. In terms of moving through water, some mosasaurs may have exhibited the more sinuous, snake-like swimming, while others exhibited the streamlined, sleek bodies indicative of tuna-like swimming and a highly agile, predatory lifestyle. Even scarier, some mosasaurs exhibit cranial kinesis, in which there is significant movement between skull bones and movement at the joint between the upper and lower jaws. Some of this movement is sliding and some is rotational, giving mosasaurs a fearsome bite and an ability to open their jaws much wider, allowing them to grab prey larger than you might expect. There's great evidence of mosasaur diets preserved in shale sedimentary rocks from the western interior seaway. Lots of ammonites and sea turtle shells punctured by the sharp teeth and powerful jaws of these terrifying predators. Finally, I've saved my favorite marine reptiles for last, the ichthyosaurs. They were some of the largest and most specialized of the marine reptiles, among the first to diversify in Triassic oceans and among the first to go extinct. By the time the last dinosaurs had evolved, the ichthyosaurs had disappeared. These dolphin-like swimmers were top predators in the marine ecosystems for more than 150 million years. The group is far more diverse than you might expect, from animals that are near-shore, eel-like, undulating swimmers to giants that cruise the ocean, rivaling the length of blue whales as the largest predators in Triassic seas. Massive anatomical changes occurred in the Ichthyosauria to transform ancient land reptiles into this fully aquatic group. Every part of their bodies was impacted, from their pointed faces to their dorsal fins and their exaggerated front flippers with intense hyperphalange, resulting in hand bones that look like corn cobs, accompanied by the disappearance of their hind legs. And then there's the hockey puck-like stacks of vertebrae that promoted side-to-side tuna-like locomotion. Some even evolved humongous eyes that indicate they were able to capture the little bit of light at great depths. The eyes of some ichthyosaurs were so big that they exhibited special bones called sclerotic rings that help support the mass of the eyes. Modern animals that have big eyes like owls have the same kinds of rings in their eyes too. Some ichthyosaurs have been preserved with remarkably detailed skin impressions, outlining their bodies in a halo that highlights their torpedo-like shapes. From these impressions, we can see that their tails included small bones supporting the bottom part of the vertical fin, but no bone in the top. This organization makes tails great at generating forward motion with little effort. But as wildly successful and innovative as they were, recent data indicates that ichthyosaurs fell victim to two climatic hits. The first came at about 100 million years ago, in the middle of the Cretaceous period, when marine waters were deepest and oxygen concentration in those waters was relatively low. Then, just a few million years later, another similar hit. Just like the extinction risk in our modern world for big specialized predators, a perturbation in ocean and atmospheric temperature may have been just serious enough to push ichthyosaurs to the end of the road. One of the coolest things about these awesomely preserved marine reptiles is a special, subtle hint about their fully underwater lifestyle. When we find these articulated skeletons of plesiosaurs and ichthyosaurs with babies, we can recognize that in all cases, the babies are being born tail first, head last. Why does this matter? Only animals that stay put in the water full time would have had such an adaptation. Compare this with modern whales and dolphins who also give birth tail first. This may seem odd, but if marine mammal babies were born head first, like in other mammals, they would risk drowning while being born because it can be a long process. Just like these fully marine mammals, by giving birth tail first, ichthyosaurs and plesiosaurs converged upon this solution to the problem of having babies drown during birth. Still, it appears that this adaptation was a difficult one for the species, since at least once in a while these animals died in the process of giving birth. Lucky for us in the fossil record, but tough for them. So, were there any swimming dinosaurs? The jury is still out on that one, but some recent discoveries in the deserts of North Africa have rekindled a long-standing debate that large-bodied theropods called Spinosaurus may have patrolled the waterways in its ecosystem in search of its next fishy meal. Spinosaurus, which means spine lizard, was discovered in the desert of the Bahariya oasis in Egypt back in the early 1900s. Its large size, sharp teeth, and distinctive vertebral spines made it an instantly recognizable superstar dinosaur. The bones from the original find were destroyed during the bombing of Munich in World War II. And ever since, this mysterious dinosaur has been the stuff of legends. New finds of Spinosaurus prompted some researchers to investigate its biomechanical capacity for swimming, with differing conclusions. Some researchers point to the fish-eating, conical, simple dentition of Spinosaurus, combined with its unusual tall and flat tail. They say that this tail could have propelled Spinosaurus through an underwater world efficiently, making it the only known aquatic predatory dinosaur. Other researchers are more dubious, noting that the tall spinous processes and resulting bony fan on the animal's back would cause too much drag for it to be an efficient swimmer. Isotopes preserved in the teeth provide hints at this dinosaur's diet. While there is a signature of fishy feasting, there is also strong evidence that Spinosaurus regularly dined on other dinosaurs and terrestrial vertebrates. Moreover, these researchers point to the details preserved in the geological record, which is indicative of estuary-like swampy environments, not broad river channels like the Mississippi or Amazon. With that giant sail on the back, these scientists argue that the only way for Spinosaurus to be an energy-efficient swimmer would be to swim at depth, which doesn't seem plausible given the geology of the surrounding rocks. Perhaps Spinosaurus stayed near the water's edge, popping its head under the surface to snatch a fish before running through the landscape in search of bigger and meatier prey. For now, we'll have to wait to discover whether there were any dinosaurs that learned to swim. But with giant marine predators guarding those watery worlds, it's pretty unlikely that dinosaurs ever took the evolutionary leap into the ocean. And besides, can you imagine a sauropod swimming, a theropod treading water, or a ceratopsian snorkeling? They could never hold a candle to those awesome marine reptiles lurking in the deep.